So we've learned how to draw Lewis structures, complex Lewis structures that can have single, double, triple bonds. What we're going to learn about today is how to draw resonance structures and how to calculate the formal charge on an atom in any given Lewis structure. So, what do I mean by formal charge? Let's start with formal charge. Well, a definition for a flashcard that you need to know for formal charge is the electric charge difference or electron charge difference between the valence electrons in an atom and the number of electrons assigned to the atom in the Lewis structure. So basically what this means, if we're going to calculate the formal charge on an atom, we need to know how many valence electrons that atom has, not in the structure, but just based on its location in the periodic table. And we subtract however many electrons are around that atom in the Lewis structure. So let's talk about an example. Let's talk about the molecule O3, ozone. The Lewis structure for ozone has 3 oxygen atoms bonded together in a linear fashion, with 1 double bond between 2 of the oxygens, 1 single bond between the other 2 oxygens, and then lone pairs around each oxygen atom so that each atom satisfies the octet rule. We can assign each one of these oxygens a number. Okay? So let's just say we call this oxygen atom on the left oxygen atom 1. We can calculate the formal charge on this atom according to the formula that we developed over here. So the formal charge on this atom is going to be the number of valence electrons in that atom minus the electrons in the Lewis structure. So oxygen is in group 6A, which means it will have 6 valence electrons. Notice, when I say valence electrons here, that's not how many electrons are in the structure. That's how many electrons would be in one neutral atom, how many valence electrons would be in one neutral atom of oxygen, minus how many electrons are around this atom in the Lewis structure. Well, there is 1, 2, 3, 4. Now the only difference here is we just care about the electrons that could be on that atom alone, so 5, 6. Each bond counts as 1, not as 2. So this atom has 6 electrons on its Lewis structure, so the formal charge on this atom of oxygen is 0. What about the middle oxygen? We'll call this atom 2. The formal charge of atom 2 is going to be, well, it's still oxygen, so 6 valence electrons, but the number that's going to change is going to be how many electrons are around it. So we have 1, 2, 3, 4, and 5. 6 minus 5. So the formal charge on that atom of oxygen is positive 1. And last but not least, the atom on the left, on the right, formal charge of 3, well, it's still an oxygen atom, so it still would have 6 valence electrons. Then let's count how many electrons are around it in the structure. 1, 2, 3, 4, 5, 6, 7. 6 minus 7 gives us negative 1. So what does this actually tell us? This tells us that although this atom of ozone is a neutral compound, it has no overall charge, it has electrons in it, which we know have a negative charge, that are not evenly distributed. Some electrons are on one oxygen atom more than they are on another oxygen atom. Well, we can see since the charge of the third oxygen is negative 1, that means there are more electrons, or electrons are more likely to be found on that third oxygen atom than they are on the first one or the second one. The other thing to notice is if we add up all the formal charges, 0 plus 1 minus 1, we get 0. And whatever you get when you add up the formal charges, this should be a rule to write down, the sum of the formal charges is going to equal the charge on the molecule. 0 equals 0. Boom. Done. What we can also see is some cool computer-generated imagery that tells us the probability of where these electrons are going to be found. Since we now know that the electrons are not evenly distributed on this molecule, on each atom, we know that one oxygen has more negative charge than the others. So we can look at something called the electrostatic potential maps. So these are electrostatic potential maps. And what this shows us here, this electrostatic potential map, is for ozone, O3. where the region that you see is red, that equals high electron density or high electron probability. Regions where electrons are going to be found. Or another way of thinking of that is more negatively charged areas. The blue areas, okay, are more low electron density, or where there's, kind of less negative, or another way of saying that is more positive charge. So what this structure, this electrostatic potential map, is showing us that in this region, so if we drew the molecule here, it's O bonded to O, O, essentially. I'm not going to draw like kind of bluish structure. We see these regions here are more red, which is indicating the electrons are going to be more likely on that region. But we also see that we have the kind of asymmetry here. There's also some high electron density and probability around this outer oxygen, whereas in the middle, it's very blue, which means it's very positively charged, more likely to be positively charged, and electrons don't spend that much time there. Well, you might be thinking, but Shar, when we drew the Lewis structure, we drew it in such a way where there was a double bond here and a single bond on one side, which meant that only one side had a formal charge of -1. This one had its formal charge of +1, and this was 0. So how do I have equal or symmetrical electron distribution? Well, the reason for that is because of something called resonance. Okay? Resonance. And what resonance is resonance is the use of two or more Lewis structures to represent one molecule. So we drew our original Lewis structure for ozone like so. What resonance tells us, and what that electrostatic potential map indicates to us, is that this molecule does not exist only in this form. We know that the formal charge is -1 on this third oxygen atom based on the molecule we drew, but we also know that this atom on the left, the red one, number 1, also has some high electron density because of the red region on the map from below. So how does that work? Well, electrons, and we now know, are waves. They can act as waves, and they can move across different atoms. They don't have to stay in the exact one place where they are. So we can move pairs of electrons. So let's say we moved the 2 electrons in this bond, and they became a lone pair on this atom of oxygen. And then let's say these electrons in this lone pair turn into a double bond between those 2 atoms of oxygen. So now, and this is the kind of notation you'll see, kind of a double-sided arrow, if we redrew the Lewis structure, we would have something that looks like this. And what we see now is that electrons have kind of shifted. The double bond is now on the other side. It's on the right side over here versus when it was on the left side over here. And you might be thinking, but Shar, that is the same exact structure. You just flipped it around. Well, it's actually not the exact same structure because each one of these oxygen atoms is a different atom. So each one is going to feel a different, pull or force or attraction or react differently depending on if it has a double bond attached to it or a single bond. So essentially, both of these structures exist in a sample of ozone. Both of them exist. And we would call these resonance structures because they are 2 different Lewis structures that represent the same molecule because they still represent O3. I could ask you to calculate the formal charge on each one of these atoms, on these oxygen atoms. And you should be able to do that at this point. What we're going to see tomorrow is how any compound that has multiple resonance structures from those multiple structures, we can predict which one is going to be the most likely to form. The most likely to form Lewis structure is going to be the one with the fewest formal charges. Because minimizing charge is a good thing for an atom. It makes it more stable. We don't want big charge distribution across the molecule. So we'll look at some examples of that tomorrow. But another way of saying this is if we have a sample of ozone, let's say we have 100 molecules of ozone, Some will look like this one on the left, and some will look like this one on the right. Experimentally, in fact, actually, we've never been able to isolate one of these. It's just too hard with, the speed that molecules move at, how fast electrons can move near the speed of light, to isolate a molecule that looks just like this. But because of experimental evidence of an electrostatic potential map, like so, for ozone, we know that those electrons have to be moving, and there has to be some kind of symmetry here, showing that there has to be a formal charge on both oxygen atoms kind of at once. One more electrostatic potential map to look at is one for water, our good friend H2O. So water, if we drew the Lewis structure for it, we're going to talk about molecular geometry later in the week to determine why this would have a bent structure. But if you notice on the map, there's a lot of red region up here, which indicates high electron density. High lone pair electron density. And if you look at your structure, there are lone pairs above the oxygen atom, which is why we have this red region here. There's no lone pairs around these hydrogens, which indicates low electron density down here. Another way of looking at Lewis structures through these electrostatic potential maps. What you need to be able to walk with today to synthesize is if I give you two different resonance structures, you have to be able to calculate the formal charge on each atom in those structures and then determine, are they resonance structures? What we'll practice with tomorrow is if I give you a set of Lewis structures, which one would be the most likely one to exist? And we know that's going to be the one that has the fewest formal charges.